Welcome to lecture 21. In this lecture, we will discuss the possibilities of using Windows as a real-time operating system. So, what would be the problems that will happen in a real system if we use Windows as an RTOS? So, how difficult will it be to extend or modify any traditional operating system to make it an RTOS? So, we'll be discussing such issues and also compare the available alternatives. So, there are two major shortcomings of Unix which pose as pretty significant obstacles. The first is that the kernel is non-preemptable. That is the first, which basically means that once the kernel executes, it executes for a very long duration. During that time, user tasks are completely cut out. So as a result, it becomes hard for them to observe their real-time guarantees. The other is that dynamic priority levels are not supported. So this makes it hard to support something like EDF. Also, in the non-preemptable kernel, even a user program can execute in the kernel mode. In the sense when it is making a system call, so as we have been discussing a dedicated kernel thread, right, where there's a one-to-one mapping between a user thread and a kernel thread, right, actually executes the code of the system call. Okay. So, in a certain sense, the user program itself can take up kernel time and kernel resources, time being the most important. So, of course, when Unix was developed in the late 60s and early 70s, the developers did not visualize the use of Unix in real time systems, particularly real time multiprocessor systems. So, a non preemptable kernel, right, is also known as a non re-entrant kernel in the sense that, once you have entered, you remain there and you get out, as opposed to a preemptible kernel where you kind of enter, you can get preempted in kernel mode, so you stay there and then you enter the kernel back again and then you execute. So whenever the system is in the kernel mode in a non-preemptible setting, we will disable all interrupts such that no task can come in the middle. And furthermore, this will also help preserve the integrity of kernel data structures, primarily because we start and we end, nothing comes in the middle. So of course this is a solution for a single processor system. It is not a solution for multiprocessor systems because on other processors kernel threads may be running and these threads may be altering the kernel state. So that is why there is a need, right, and that too a significant need to look beyond this traditional non-preemptible kernel ideas, where what we do is that we disable interrupts and enable them. But again, as I said, this solution is primarily a uniprocessor solution. It is not a multiprocessor solution. So if we talk about a reentrant kernel, so basically if you consider a process, so it can be in user mode. Let's say there is an exception. And then again, it'll come back. Then let's say you're processing an interrupt. Okay. But the moment you're processing an interrupt, let's say another interrupt comes up, which has a higher priority, then that is processed. And again, we go back to resuming the earlier interrupt processing. And once that is done, we come back to the process, right? Or we run another process. So this is the idea of the reentrant kernel, where many of the kernel routines themselves are preemptible, which means that several processes may be in the kernel mode at the same time. The kernel can suspend the currently running kernel thread or currently running kernel process, and then again it can restart it later. So such reentrancy is of course required when we have deadlines associated with interrupt processing and deadlines associated with user mode tasks. So for example, we would want a user mode task, for example, to have a higher priority than, let's say, interrupt processing. Because as you have been seeing in the earlier part of the chapter, we made scheduling our primary method, our main method, of actually implementing any system was based on scheduling only. So for a non-preemptable kernel in a real-time application, this can cause deadline misses as we have been arguing. And the task preemption time will basically be equal to the time that is spent in the kernel mode, which can be quite long actually if the kernel itself is not willing to be preempted, plus the context switch time. This is exactly why we don't want this kind of a design. We would want the flexibility of suspending the kernel in any time at the cost of a user task if it is doable, right? And given the fact that the kernel often does a lot of work which is unrelated to the currently executing task, it could be some garbage collection or bookkeeping, such times can be fairly long, right? So, given the fact that such times can be fairly long, this is a matter of significant concern. Also, the issue of dynamic priorities. So, the Unix scheduler does maintain a multi-level feedback queue. Where, as we have discussed in the earlier lecture, we have several user priorities, then several kernel priorities, and even within that, the disk IO and buffer and IO intensive tasks have more priority. So the system by default uses a 100 millisecond scheduling time slice. So this has been discussed in great detail in the previous lecture. I'm not going through it. So basically, we discussed this when you're talking about software clocks that every process is given 100 milliseconds to execute. Once it finishes it, its budget is exhausted. So in a round robin fashion, we go to the next process. Then we have task priorities, which are recomputed after each interval. So the Unix scheduling policy as such is simple. So if let's say we are looking at the priority of task Ti for the jth invocation, so then I stand corrected is at the jth time instance. So this will basically be the priority of the CPU for the priority of this task on this CPU. So in a sense, it's like its affinity. The base priority of task Ti plus the nice value. So it is possible that the task itself may be nice to other tasks and deliberately reduce its priority. So in this case, what happens is that higher is the number, lower is the priority. So if I add a positive nice value, which I always can, in a certain sense, I am being nice to other processes. All right. So given the CPU priority, CPU Tij, this is basically a weighted sum of two variables. The first is the CPU priority at the j-1th time instant for this task, and the other is the utilization of the CPU in the j-1 to j time instant, right? So basically, higher is the utilization, higher is this number, and as I said, higher the number, lower the priority. So in a sense, if you have used the CPU more in the past, then we kind of reduce your priority such that other processes, other tasks also get a chance. So priority Tij is the priority of Ti at the jth instance, and CPU Tij is basically a weighted sum of the CPU utilization at the j-1th instance and the instantaneous utilization. All right. So basically, the history of CPU usage, we can unfold this recurrence. So this is what it will come to, right? Plus if I take it to j-2 and so on. So you can say that the recent utilization has the highest priority. The one after that has slightly lower, right? 50% of the weightage of this. The one before that would have at j-2 like u ti j-2 would be divided by 8. That would have 50% of this. So we are kind of assigning weights geometrically, right? For the past CPU utilization history. So also now coming to the base priority that we had in that equation. So different base priorities will segregate our tasks into different bands. So we had looked at the swapper, the block IO system, file manipulation, character IO, and kernel processes, and then user. So if you would see, all the IO centric tasks or all the IO centric processes are the ones that have an elevated priority as opposed to regular processes which have a reduced priority. All right. And then, of course, we have a multi level feedback queue in the sense tasks and processes can move among these queues. So, the central idea is that IO speed is very slow as compared to CPU speed. IO is the bottleneck. So, it is important to keep IO channels as busy as possible. The only way to do that is to raise the priority of the IO intensive tasks such that you keep IO as busy as possible, and once IO is happening, you go back to your CPU jobs, right? So that's the key idea. So what happens is that IO bound tasks will then gravitate towards higher priorities. So if a real time task spends most of its time doing computation, so you would see that it is at the receiving end of this priority assignment system, because IO tasks will get most of the CPU time in this regime. As a result, compute heavy real time tasks may miss their deadline. This is clearly unacceptable. So, Unix 5 as a real time operating system is suitable, well, mostly unsuitable, but even if you want to use it for soft real time applications, not hard real time applications that could have deadlines that are of the order of milli or microseconds. There are other, if I look at the deficiencies, it is basically the task preemption time, which can be large because of the kernel overhead. Dynamic priority computation is not there. And also, the resource sharing problem. This is not adequately addressed in the sense it doesn't implement PCP, where high priority tasks may wait for low priority tasks that are holding on to their resources. Other deficiencies, again, we have discussed inefficient. Well, inefficient is a strong word, but the key point is that it is not preemptable. So, non preemptable interrupt processing. And then, we don't have adequate timers and lack of real time file system support. So, now coming to Microsoft Windows, which started out primarily as a microkernel based design, but as I said, it's somewhere between monolithic and micro. There is a very growing market. Okay, so it's not as big as people would have liked it to be, but nonetheless it is growing. So it started with the Windows CE versions of Windows. So after Windows NT came in the late 90s, it has been extremely stable with support for POSIX APIs and multi-threading. It has definitely evolved from the naive uh, DOS disk operating system. So DOS, of course, was a very simple OS, single tasking, right, with segmented memory management. But Windows has all the features. So it has a graphical front end. Then it has a lot of code, and as you can see, now it has become the de facto operating system, the most popular operating system, at least in the desktop and laptop segment. Of course, what is being assessed over here is whether it is the best for real-time systems. So that's the reason I'm just slightly going through the history. So as you can see, we are actually at Windows 11 now, 9, 10, and 11. But it has really grown. It has really grown over the years. So the key point is that because the idea was that we need to support a lot of devices, it was primarily the design philosophy was a microkernel based design. But of course, now things are, the operating system is way heavier than what it used to be in the past. So coming to Windows NT, let us look at its main components and what provides the base services. So we have an NT microkernel, which provides the basic services. Then we have an executive. So it builds on these base services, to provide more advanced user level services. And what are these user level services? So they are used by, again, of what is called as subsystems. So subsystems are privileged subsystems which again run in a privileged mode. They are a part of the operating system, right? So we have three layers. We have layer 1, which is the NT microkernel, layer 2, which are the basic base services, and then we have the subsystems, which is layer 3. So as you can see, it's a layered microkernel kind of design with a microkernel at the center. Then of course we have user programs, right? So the same thing is shown over here. There is of course a hardware abstraction layer which all operating systems should have. So Windows also does have it. It's not shown. But the key point, even in modern versions of Windows, is that there is a microkernel. On top of that, we have an executive. Then there are different subsystems. They could be in the user mode, could be in the kernel mode, or could be kind of in both. So we have subsystems for 32-bit Windows, POSIX mode, and so on. So these subsystems then support user processes which run on them, and subsystems are kind of at the boundary of the user and kernel mode. So coming to the NT executive, it provides higher level services than the microkernel, and it runs in kernel mode, but it is not the microkernel. So this makes it easier to maintain, and it itself is built of independent modules. The good thing is that the microkernel, of course, is kind of inflexible here, but all the modules of the NT executive are independently, pageable and preemptible. So let's discuss what these are. So preemptible is basically that they can be preempted. Again, that's a good thing. And the fact is that they are pageable. So pageable basically means that they don't hog physical memory. So they can be stored in virtual memory. So if whenever there is an issue of capacity, that is when these pages can be moved out. But again, that does cause real-time problems. But given that these modules are preemptible, the situation is not that bad, right? So we don't actually get to see it because it becomes a preemptible task. So this is a diagram of the simplified Win NT architecture. So as we can see that the lowermost layer or the lowest layer is the hardware abstraction layer. Then we have the kernel and the device drivers, and on top of that we have the executive. This is something that we have been discussing quite a bit in the previous slides. And we also have the windowing and graphics subsystems. So in the case of Windows, these are in the kernel. They are not in the user space. They are in the kernel. So which ensures that we have a better graphics experience, right? So for a long time, Windows had a much better graphics and graphical experience than Linux. And this was a reason that graphics was built into the operating system. Then in the user mode, we have the subsystem DLLs, user application, service, and system support processes. So, well, one nice thing is that many of these service and system support processes have gone into the user mode. So, this ensures that real time user threads can compete with them and also can have higher priorities. So, this is a slightly deeper look from the book, from the OS book of Galvin and Shilberschatz. So, we have the hardware abstraction layer, the kernel, right? So, the window management system and graphics is over here. And what we have as a part of the executive is basically the IO manager and a bunch of other managers that we will look at. So IO manager, has both the device drivers for the storage devices, network devices. Along with that, it has the file system and the file system cache. So all of them go together because they are interrelated. And for the executive, our main aim is a more or less microkernel based design. So here we have the object manager because everything inside Windows is an object. So we use an object manager, security, process manager, plug and play device manager, virtual memory manager, and a local procedure called facility. So this is a very low overhead kernel procedure call facility that Windows provides. Then on top of that, what Windows provides is it provides a bunch of services and subsystems. So for example, for a subsystem, we can run POSIX applications on the POSIX subsystem, which basically does the job of translation, right, from a POSIX call to a Windows call. Similarly, we have the MS-DOS subsystem to allow us to run MS-DOS applications on Windows. And the same holds for legacy OS 2 and Windows 16 applications. And along with that, there are a bunch of system processes and subsystems which run in the user mode, which is a good thing from at least our perspective. From the perspective of real-time systems, these are good things. So these include the logon process, security subsystem authentication, and the security account manager database. So the key system components, again seeing the same diagram once again, would be the hardware abstraction layer, executive, the different subsystems as we have seen. They, in a sense, allow us to run binaries and executables compiled for either a different version of Windows or an earlier version of Windows, like the POSIX compliant Windows or Windows 16 or MS-DOS or something. And then we have system processes and user processes. So this is where you can see elements of the microkernel design over here and over here. So the same thing. Once again, I will not look at in more detail, but one additional thing that has come up in this diagram is the system threads. So the system threads run various aspects of the Windows subsystem. Run various aspects of the kernel and executive inside Windows. So the kernel itself is multi-threaded, and then we have this large DLL here known as NTDLL. So the role of all services and user applications is to use this for whatever services they need, at least at the user level, or to interface with the kernels. As you can see, a lot of system processes, a lot of services, applications, and environments load the code from this massive DLL, which provides a nice abstraction on top of the kernel. So as we have seen in the Windows OS architecture, we can have multiple personalities. So what is a personality? The personality is basically these environment subsystems over here, in the sense we can either use a version of Windows natively, or we can have a binary which is compiled for a slightly different environment, be it Windows 16 or POSIX or MS-DOS. So this specialized bespoke environment which Windows supports, this is known as a personality, which means user applications do not call the native Windows operating system services directly, but instead they call special layers. They call special DLLs, right? Which do the role of translation. Again, this adds some overhead, but this is primarily made for the sake of flexibility. Then we have the DLLs for the specific subsystems, which means that do the role of translation, in the sense, let's say I have the MS-DOS subsystem and I have a system call for MS-DOS. So then this job of translation is done, where an MS-DOS system call becomes a Windows system call. So the role of the translation is done over here. Furthermore, environment subsystem processes that we have seen for OS 2 or DOS or Windows 16, they manage client processes in their world and also impose a certain semantics on top of them, because actually if you think about it, so MS-DOS did not really have a process model or a security model which was as advanced as Windows. So one key role of the environment subsystem is to impose this discipline on top of whatever environment the programs were natively compiled in. So originally there were three environment subsystems for Windows, POSIX and OS/2. So Windows 2000 included Windows and POSIX. So Windows XP of course then discontinued some support. So it included only different versions of Windows for backward compatibility. And it had an enhanced POSIX subsystem which is available for certain services with Unix, where some POSIX compatible binaries could run. So the key point is that whenever we are importing binaries from another subsystem and running it on top of Windows, there is a need to impose some kind of discipline on the threads, particularly for the process model and security. And naturally, any Windows scheduler will have to take that into consideration and ensure that if there are real time deadlines associated, they are not violated. So, the kernel mode components, as we have seen, the two main components are the executive and the kernel. So, the executive runs at a slightly lower priority, which again is an artifact of the microkernel based design. So, it provides basic functionalities for memory management, process and thread management, security IO, and interprocess communication. So, essentially, the key features of a regular Linux kernel are all a part of the executive. So, what is there in the kernel is basically something which is at a lower level as compared to the executive. So, these are very basic scheduling, interrupt, very basic scheduling mechanisms and interrupt processing mechanisms. So, for example, all the interrupt top halves, methods to deal with interrupts, basic scheduling, and synchronization, right? So, the main is scheduling, synchronization, and interrupts. That's the way you would like to view the Windows kernel, that it does things which are very basic. It provides the very basic primitives, and then it's a layered architecture where different layers build on top of it. So it basically provides a set of routines and basic objects which would be used by the executive, the kernel processes, user level processes, and the subsystems to implement a full featured OS. And in some version of NT, in an older version, it was all a part of the NTOS kernel.exe. But these things again, keep changing with the OS version. So the kernel mode components or the drivers, which, as you have seen, sit parallel to the executive and the kernel. So if this is the executive kernel, so the drivers would sit over here. So the .sys files are the device drivers whose job is to translate between user function calls and hardware calls. Then we have the Windows and graphics driver, which has a very central position in Windows as opposed to a Linux like operating system. So that is win32k.sys. It provides GUI functions, which are all the regular functions that we see for windowing, user interface, controls, drawing, etc. And then we have a hardware abstraction layer, which actually sits below the kernel. So the main role of the hardware abstraction layer is to isolate the kernel and the executives from the nitty-gritties of the hardware. So it is again a very thin layer which virtualizes the hardware to at least some extent, such that the kernel can run on top of it. Because what we need to understand is that the Windows kernel is meant to run on a large variety of hardware, right? So maybe not as much as Linux, but at least all kinds of Intel x86 devices. It runs on ARM these days as well. So that is why there is a need for a hardware abstraction layer, right? So it hides platform specific differences, primarily differences in the motherboards. Then we have background system processes, right, which again sit at a higher level as compared to the executive. So these are at the user space, the logon process, session manager, etc. in the user mode. Sorry, these are in the user mode, not in the executive. These are in the user mode. And then we have service processes whose job is to provide services to other processes. So again, some of these are in the user mode, some are in the kernel mode. So we have the task scheduler. This is a part of the executive. We have the spooler. So spooler, some versions of it can be in the user mode and some in the executive, which is in the kernel mode. And then of course we have a bunch of Windows applications, all in user mode, which provide services to other Microsoft applications. For example, Microsoft SQL Server. So that provides services to any application that needs database services. Then we have the Microsoft Exchange Server, and we have many such components, right? So it's pretty much an ecosystem that builds on top of each other, where a bunch of service processes provide a lot of service to other running user applications. So how was such degree of portability achieved that given any motherboard Windows can run on it? So most Windows code and device drivers are written in C. C is tied to the hardware to a large extent, but the point is that all the hardware specific code is pretty much limited to the hardware abstraction layer and the kernel, right? And this can also contain some degree of assembly language code. So this is something which is specific. So in a sense, what happens is that given the fact that the Windows source code is not open, at least I can tell you from my experience on Linux that there are different subdirectories for different kinds of hardware. For every kind of hardware, so in Linux is actually different processor types. So in the subdirectory, there is a specific assembly code snippet for a given set of processors. So this, in a sense, virtualizes it because after that, the layer above the abstraction layer doesn't actually get to see the idiosyncrasies of the hardware. And then at a higher level, instead of C and assembly, the components are written in C++. And nowadays they are written in different .NET languages like C Sharp and so on. So that this is again at the highest level, where of course we are not interested that much in performance and a linkage with hardware, right? So we are interested more in portability and maintainability of the code. So examples would be the Windows graphics subsystem driver and the storage volume manager, right? So they all migrated to C++, and something in the application layer would use C Sharp .NET these days. So is Windows really a microkernel OS? Well, no, not really. It's not a pure microkernel OS. So it is true that many OS components and drivers run in separate private address spaces. They are not really allowed to access the kernel address space for security reasons. A lot of components also are run in user mode, but the point is that all kernel components particularly share the address space, and in many cases there is really no protection between the OS and the drivers. And this is why this is not a pure microkernel, but again, it is not as monolithic as Linux or Unix, for instance. So, what makes it similar or more similar to a microkernel OS? Well, the first is that OS personalities. So, as we have seen in MS-DOS personality or an OS2 personality, where OS2 was an old IBM operating system. So, these run in user space as separate processes, and then applications can use them to run on Windows. Many kernel mode components will not access each other's data structures directly. They will use what are known as local procedure calls to pass parameters. So in a sense, it's a messaging based system where there are strict rules on the kind of messages that can be sent. Again, there is a reason for this. Windows actually uses a large amount of hardware. Given that it uses so much of hardware, it becomes important that security and a degree of isolation is maintained. That is why it is called a modified microkernel. Again, why was a pure microkernel design not used? Well, again, performance reasons, software engineering reasons, that if we have separate address spaces, anytime we want some help from the OS, This would require a context switch or some kind of protected messaging which has its overheads. So many other commercial OSs, Linux and so on, are also moving away from a pure monolithic design and having some microkernel concepts. But a pure microkernel as such doesn't exist in the commercial space as of today. So coming to Windows NT and the priority levels, we have 32 priority levels with a real-time class and a dynamic class. So a task cannot move between these two classes. So these classes are mutually exclusive. And whenever a priority level of a task changes, so when does it change? When you iconify it, which means when you minimize it, right? So if a task is running and the task is, you just click the minimize button, it goes to the tray icon, which means it doesn't remain a foreground task. At that point, the priority of the task changes. So of course, the lowest is the idle process, which means that nothing is running. And then we have our regular user processes, which have a dynamic priority in the sense that over time, for example, if you minimize the window, the priorities change. So we can have low foreground. Low foreground means that it's running in the foreground, but it has a very low priority, like a calendar app or something on the desktop. We have a normal background process, whose graphical user interface or GUI we are not seeing. And then we can have a normal foreground process like a text editor or browser. And high foreground would be something like a game or a video, which really needs a lot of CPU time. On top of that, we have a real-time classes. So in this case, higher the number, higher the priority. So again, we have three types: real-time idle, which basically means that you're not running a real-time thread yet, but still the CPU is reserved. Then real-time normal and real-time critical. So actually, in the case of Windows, we have a matrix of priorities. So consider a real-time process. If it is idle, we give it a number 16, because finally, for every process, we have to give it a number which is between between 1 and 31. So the point is that the way the numbers are assigned is this is the way they are assigned for real-time processes: 31, 26, 25, and so on. For high priority process, which is still in user mode, we give it numbers which are high, like 11, 12, 13, 14, above normal, slightly lower. Again, in this case, for all the non-real time processes, the idle process has priority 1. And for a normal process, this would be our priorities: below normal and again idle. So, how do we process interrupts? So, well, when an interrupt occurs, the interrupt handler routine saves the machine state as it would normally do. It executes the interrupt service routine. Again, no surprises in that. And again, no surprises in this, that similar to Linux and all other modern operating systems, the critical or the most important processing, which is known as the top half, this is something that is done with a very high priority in the kernel. The bottom half can run as a part of the executive with a much lower priority, which does the bulk of the work. And the top half has high priority mainly because an external device is involved. So we need to set its state correctly. All right. So the bottom half in the case of Windows is known as a deferred procedure call or a DPC. So the layered architecture that we have is like this: that on top of the kernel we have the executive, which again runs in protected mode because it provides basic system services. On top of the executive we have several services. So we have a modular structure, right? So given that the kernel and the executive are fixed, we can add different services and different subsystems on top of them, right? So this is doable. Then we have the kernel, which is always kept in memory. It's never paged out. The execution is never preempted. So the main responsibilities, as I have said earlier a few slides ago, are thread scheduling and interrupt processing and synchronization. So of course the kernel also manages the key parts of the boot process and the recovery after power failure. So interrupt handling is like this, that let's say that we have a high priority task that is executing. The moment there is an interrupt, the interrupt service routine comes in. So this is the top half of the interrupt, and then the bottom half is scheduled for a later time. It is known as a deferred procedure call or a DPC on Windows. So then the high priority task finishes its execution. It terminates, relinquishes the CPU. Then the DPC, which is the bottom half, which has the normal priority, is scheduled later, right, on the CPU. So this is how you can see that the real-time nature of interrupt processing is there. Deferred procedure calls are pretty much queued in a in a FIFO first in first out queue. They are processed at the same priority level, right? So basically, the problem that comes over here, which is something that ideally should not have been there in a real-time operating system, is that the priority of a DPC should be, in a sense, commensurate with the priority of the process that led to the DPC happening, right? Either the source of the interrupt or the target of the interrupt. Because what normally happens in Windows is that the execution of a real-time thread can be affected even if you have very unimportant DPCs executing. For example, consider a very low priority process. Its page fault is executed at a very high priority, right? Which is even higher than a real-time process. And this is exactly what causes problems and deadline misses, right? So this is something that Windows does to harm real-time systems, at least the versions that we are aware of. So DPCs would typically perform network or disk IO, and this may lead to an unbounded response time for real-time tasks. And here again, the reason that they would lead to an unbounded response time is primarily because of low priority DPCs hogging the processor. So Windows has a real-time has an embedded version called Windows C, which actually uses a priority inheritance scheme for DPC. So this avoids priority inversion, it avoids unbounded blocking and so on. So DPCs still operate at a priority level normal, right? Not at a low priority level. But a DPC of a higher priority process is raised to indicate the priority of that process. So what are the main shortcomings? Well, one shortcoming that we are just seeing is the lack of predictability in interrupt handling, right? So this is clearly a shortcoming. The other is that the priority ceiling protocol, which is needed when we have real-time threads with resource dependencies, right? Resource access control, this is not there. And then, of course, we could have distributed applications in the sense, multi-threaded applications or applications that are running on many Windows nodes that talk via the network. So such applications have little support, right? So again, interrupt handling, unbounded priority inversion possible, right? In this case, basic priority inheritance is also not supported. So this finishes the lecture on Windows NT. So we will continue to look at other kinds of real-time operating systems in subsequent lectures.